In this lecture, we're going to talk about and learn about heat diffusion and heat vaporization, and the best way to go about dealing with those constants. And the constant we're talking about today is for water. So we're going to talk about specifically the heat of fusion, and fusion is a fancy word for melting, believe it or not, and the heat of vaporization. Now these are constants, as I talked about, and they're very important because they help us measure energy that is normally difficult to do so at the phase changes. To understand heat diffusion, heat of vaporization, you really need to understand how they came up with these constants. Let's first talk about why we need these constants. First and foremost, as we review the heating and cooling curve, let's dealing with the heating curve of water, we have the solid phase, and we know we have pure solid phase when the kinetic energy goes directly up. We know that when we have a phase change, it's a solid turning into a liquid, we know that the kinetic energy is converted to potential, and we have both phases present in equilibrium. Then we have the pure liquid phase. Once it all melts, it becomes a liquid, hits a particular temperature, and the liquid, of course, goes into a phase change, going to a gas. Okay, notice this line is longer, and then we go into a gas. I'm not really going to review those points. I have another lecture that does that, but we know previously that we have this equation for heat. We've been using it for many equations. Q equals mc change in T. Now in this thermal equation, we have change in temperature right there. And where do we have change in temperature in our heating curves? We have a change in temperature if you've got a pure solid phase, you have a change in temperature pure liquid phase, and a change in temperature in the pure gas phase. Now, with this change in temperature, we can use this formula. So anytime you have a pure phase, whether it's solid, liquid, or a gas, okay, we use mc change in T. mc change in T, and of course, mc change in T. So I can use this formula, okay, for any time I have a phase, a pure phase. Understanding why? Because there is a change in kinetic or average kinetic energy, which is temperature. Okay, so we've been dealing primarily with calorimetry problems, dealing with the water in the liquid phase and using the Q of water equaling what? The Cheeto, the ice cube, different things, because we had liquid water. But when we deal with a phase change, we know the kinetic energy stays constant, the temperature stays constant, even though in this case energy is being absorbed. We've talked about the why. So we can't use this formula because there is no change in temperature at the phase changes. Okay, we can't use that. So we need a formula that helps us, or at least a constant that helps us measure energy at these phase changes. So what we do is we do calorimetry. And in class today, or in class that I will be doing, or maybe your teacher will do if I don't have me as your teacher, you're going to take a very simple cup, maybe a NASA grade calorimeter, that's what I call a coffee cup, and you're going to add some known amount of water. And let's pretend we have 100 grams of water. Okay, let's go back a little bit. All right, sorry about that. 100 grams of water, and in that 100 grams of water, let's say the temperature of that water is 20 degrees, 20.0 degrees Celsius. Okay, now I'm going to drop an ice cube into the water. All right, the ice cube we're going to pretend is at 0 degrees Celsius, and I'm going to talk about why that's important. Okay, we're going to assume that we're at 0.0 degrees Celsius. Okay, and the assumption we're going to make is the ice is going to melt. Now, melting, of course, is when the solid goes directly into the liquid. So, of course, that is occurring right here. That is where we're having the solid go to the liquid. Okay, now, we know it's endothermic. We're going from a low energy state to a high energy state, so we need energy to make that happen. So we have H2O, solid, plus energy, I'll just leave it as E, goes to H2O liquid. It's endothermic. Energy is in the reactant side. So clearly, we know because melting is endothermic, energy is going to flow from the water to the ice cube. All right. Now, so in this scenario, we're going to say Q of the ice, which is the energy of the ice that's absorbing, has to equal the Q of the water that is releasing the heat, right? So it's basically energy absorbing, another word for it is consuming, equals energy releasing. You can't have one without the other. Someone has to absorb, someone has to release. Now, because the ice, okay, is melting and there's no change in temperature at a phase change, we can't evaluate the Q of the ice using the old formula Q equals mc change in T. Can't do it. So that renders our ability to directly measure how much energy the ice is absorbing. But because the ice is absorbing the same energy that the water is releasing, that's conservation of energy again, we can evaluate these joules based on how much water we have. So because Q is mc change in T, I have 100 grams of water. We know the specific heat is 4.18 joules per gram per degree Celsius. Make sure you write your units. And I'm just going to guess these values. We're just doing this as an exercise. And let's say the temperature went down 10 degrees. So it went from 20, and after I put the ice cube in, lo and behold, the final temperature, TF, equals 10 degrees Celsius. So 20 minus 10 is 10 degrees Celsius. Okay, so when I multiply this out, I get 4180 joules, right? Everything cancels except my joules. Okay, and this would be very helpful for knowing how much energy it took for this ice cube to melt, but not very helpful beyond that, because what if I have different size ice cubes? Remember, what I'm trying to do is come up with some kind of standard or constant that I could help me measure the energy when there's no change in temperature. We know there's an absorption of energy because these things create colder environments because they're endothermic, but we can't see a change in temperature. Okay, so what we do is we take this total energy, okay, and we're going to divide it by how much grams of ice cubes we have. Just like we've done in previous labs, we found the amount of kcals per gram of fat in a Cheeto. Okay, this time we're finding the amount of joules absorbed per gram. That's important because in lab, if you do this lab, and we did this in our class, we're going to have different size ice cubes. What good is this number unless you compare it to some standard? So we're going to compare our value to every ice cube ever been made of all time, okay, by dividing by the grams of the ice cube that actually dissolved or melted, okay? So I can do that. So let's pretend I'm a princess and this was 10 grams. So let's pretend this ice cube was 10 grams. So 10 grams of ice cube in water created an energy imbalance of 4,180 joules. So that's how much energy was absorbed endothermically by the ice cube. But what good is that again if I don't know how much ice cube? So by dividing it by the grams and getting this joules per gram value, now I have a constant no matter what size ice cube. If I do this very carefully under controlled conditions, everybody will come up with the same value because the energy per gram. Any case, do the math and you get 4118 joules per gram. My friends in chemistry, this experimentally I just did is my heat of fusion. Now, of course, that's what I made up here. Now, what does that mean? Well, if I had 2 grams of my ice cube, right, and I want it, as long as it's at its what? Melting point, which is 0 degrees Celsius for water at standard pressure, long as I'm here and going to here, all I have to do to figure it out is do what? Well, take my 2 grams and times it by my heat of fusion, which in this case is 418 joules per gram. And looky here, party people, the grams cancel and I'm left with total energy. Okay, so this would be 836 joules, and that's how much energy it takes to melt 2 grams of ice. Look at that, I have a new formula. Q, which is total energy, is equal to the mass times heat of fusion, which we got by doing calorimetry. We got this standard. This would not be a standard because it depends on the size of the ice cube. No longer does it if we divide by the size of the ice cube. So now we have another formula, my friends, in chemistry. We have Q equals mass times this standard. I'm going to put it in right here. So at the phase change, I have new formulas, and they are mass times your heat of fusion, as long as you're at the what? Phase change temperature from here to here only. I may say, what about this one? Well, if we do another experiment, okay, I'm not going to go through it all, but I had liquid water becoming liquid gas. So if it was liquid water going to gas, and I measured how much energy it takes for a liquid to become steam or vapor, we would come up with a total value. We would divide that by the grams of the what? Grams of not the ice but the steam, and we would come up with a value of joules per gram, and we'd call that heat of vaporization. So this would be mass times heat of vaporization. And these two standards are for specifically water. And we have them written down for you in your reference table. Let's go there. So if we look at our reference tables for chemistry, and we see that table B is going to give me my physical constants for water. And lo and behold, we have our heat of fusion, which is the joules per gram here, and the heat of vaporization. Notice something, that the heat of vaporization is much larger than the heat of fusion. Remember, heat of fusion is the amount of energy it takes for 1 gram of ice, H2O liquid, solid, to go to H2O liquid at the same temperature. Now, it's also the amount of energy released as water becomes a solid, right? Heat of vaporization is the amount of energy it takes 1 gram of liquid to go to a gas. But it's also the energy released as a gas becomes a liquid in terms of water. Now, these are for water. If they're not water, you would need new values. Okay? Now, why is this so much bigger? Well, we've touched upon that, haven't we, in other places. It's the same reason why this line is longer. If this is the amount of energy per time, if we're saying that for every 1 minute there's, I don't know, 100 joules being absorbed, okay? Sorry, big fingers. Okay, if 100 joules of energy is being absorbed, then this line being longer means it takes more energy to convert a liquid to a gas. So we've talked about that. So the heat of vaporization is always going to be bigger because it takes a lot more energy to make something that has many degrees of freedom than a liquid does. And of course the gas with tremendous high potential. So we have another formula, and that's Q equals mass times heat of vaporization. And we're going to do 2 labs. We did one with the melting of ice. We'll do another one with heat of vaporization. Okay, but these are our 3 thermal equations. If you have a pure phase, that means you have a temperature change because the kinetic energy can change. We're going to use our old formula. If you have a phase change involved with your thermal equation now, we have these 2 equations, but understand, we need the constants. The constants are given to you, but they're specific for the type of substance we have. We're most of the time dealing with water. Okay, and that's how we deal with this. Now, for the types of equations we're going to deal with now, I'm going to mix and match some questions that deal with a change in temperature or combinations of the phase change with changes in temperature. It's very helpful to do these problems with this curve in your mind. So let's go to the worksheet I gave for homework. Okay, now that we have the worksheet that I gave for homework, let's look at question number 1. Question number 1 states, how many joules of heat are needed to melt a 500 gram ice cube at its melting point temperature? Some very important points here. We're screaming to you, I have an ice cube in the solid phase, and they're telling you grams. But here's the thing. We want to, what? Melt it. That's a phase change. At its what? At its melting point temperature. So that's screaming to you that we're at a phase change. Of course, very quickly, heating and cooling curve. What does that mean? That means we are right there. And at its melting point temperature, that means I'm between this point and this point, and since it's ice cube, it's water, it's 0, okay, degrees Celsius. Okay, I know I'm using m times heat of fusion. So very simple. So Q is equal to the mass times the heat of fusion, which is that constant we get from calorimetry. And of course, 500 gram ice cube times the heat of fusion. Now we're going to use the one in a reference table as 334. Put the units in, guys, joules per gram. Notice what's going to cancel. Grams go. And let's go find our number. Okay, I get 16.7000, or that's of course joules, because everything cancels but joules, or I can convert that to 167 kilojoules. That's how much energy it takes to melt that ice cube at its melting point temperature. I could not use Q equals MC change in T because there's no change in temperature at its melting point temperature. Okay, let's move on. That's pretty simple, straightforward stuff, and that's a Regents level question. We'll move on forward from that. Number 2, let's read this question. A 50-gram sample of water at 20 degrees Celsius has 5.2 kilojoules of heat added to it. Calculate the final temperature of the water. Well, if you read carefully, where are we on this heating curve? We have a sample of water at 20. So that means, well, if this is going to be our solid, this is our liquid, well, this is the melting point temperature. We're well above that. And we're going to add heat to it. What's the final temperature of the water? Well, we're adding heat. It's going to get warmer. So if you notice, we're on the temperature change here. So what are we using? MC change in T. So this would be Q equals MC change in T. This has nothing to do with a phase change. So this would be an older style problem that we've covered already. But to evaluate it, it's very helpful to write this. So I'm not going to do this problem. I have the key posted. But you can see that this is not going to have any phase change or heat of fusion, heat of vaporization involved here. Let's go on to number 3. Calculate the joules of heat released as 10 grams of steam at 100, okay, condenses to water at 100. If you want to try that, you can, and pause this. Pause it now. Okay, we're back. So if you didn't pause it and you want to see me do it, well, I know that at this heating curve, did they mention or make any hints in terms of a phase change? They did. They said, I have 10 grams of steam at 100. I'm at that phase change temperature for water. They said it again, it condenses to water at 100. So look at all these keys here. So they're saying I am at 100 degrees Celsius, which we should know is our phase change temperature for condensation or boiling. Now, of course, I drew a heating curve, but we would be going the opposite way in this case. Okay, condenses, it's another phase change to 100. So we're between here and here. So the formula, of course, is mass times heat of vaporization. We need this constant here, which is going to be higher. Of course, we talked about that than the heat of fusion. So Q is equal to mass times specific heat change in temperature, correct? Of course not. There's no change in temperature at a phase change. So it's mass times the heat of vaporization. Pretty simple stuff. Okay. The mass, of course, is 10 grams. Okay. And the heat of vaporization, if you don't remember what it was, we go to table B. And in table B, we have 2260. That's our heat of vaporization of water, joules per gram. So let's use that. Okay, so 2260 joules per gram. So much higher than the heat of fusion for obvious reasons. Okay, so let's go find that. Grams cancel, and I think we can do this with a calculator. 22600, and that'll be joules, okay? Or it could be equal to 22.6 kilojoules. Not really concerned about, well, this is 2 sig fig, so this would be 23 kilojoules. Okay. Pretty simple stuff. Notice we're at 100 though. We're just at this point. Okay, let's go on to number 4. A 3-gram sample of water at 6 cools to 1. How many joules of heat were lost? Are we at a phase change? No, of course not. So of course we're at Q equals MC change in T. There is a temperature change. Where are we on the heating and cooling curve? We're at the what? Just the pure liquid phase. So we're here. So it's MC change in T because there is a change in T here. Okay? So we're going to plug that in, and you can do that in your own time. Let's continue on. Okay? Number 5, calculate the kilojoules of heat needed to convert 3 grams of water at its boiling point to steam at the same temperature. I'm going to let you do that for homework. Okay? And I want you also to finish number 4. Let's do another one over here. Okay? Let's try some of these. Number 6, a 25-gram ice cube is placed in 1,000 grams of water at 30 degrees Celsius. Calculate the final temperature of water after the ice cube is completely melted. Well, I'll let you finish this one. This is much like what we did for lab today. We have a 25-gram ice cube. It's placed in 1,000 grams of water at 30 degrees. I want the final temperature of the water after the ice cube is completely melted. Now, I will say this. Q of the ice equals Q of the water. All right? Now, the water is going to be MC change in temperature. The ice, because you know it's 1,000 grams, can't be MC change in T. We know something. We can do the melting of ice. Melting of ice is mass times heat of fusion. So you can take your 1,000 grams, times it by the heat of fusion, which is 334 joules per gram. And then with the mass of the water, ooh, I did something wrong. Bad Grotsky. I have a 25-gram ice cube. Sorry. Feel bad. Now I'm over it. Didn't feel right. 25-gram ice cube. Remember, it's a Q of the same. No mixing and matching, like I almost made a mistake there. And of course, 1,000 grams of water. Specific heat, 4.18 joules per gram per degree Celsius. Now, the water is getting colder, so the final temperature is going to be lower. So TI, which is 30, minus TF, and you can solve that way. All right, pretty straightforward stuff. Now, today in lab, we couldn't do this, right, because we didn't know this value yet. So that's how this one is different. Go solve for that one. Let's continue on. Number 7. All right, now I'm going to have some fun. Number 7, how many joules of heat are required to completely melt 15 grams of ice at 0 and heat to 30? Okay, so let's draw our heating and cooling curve. And what do we have here? All right, first and foremost, we're going to melt 15 grams of ice at 0. That is happening right here. At 0 degrees Celsius, we're melting, so we're at the phase change. We all should know that's M times heat of fusion for obvious reasons. Now, not only are we going to melt it, we're going to go from here to here, we're also going to go to where? We're going to heat it to 30. So we're going to melt it first, and then we're going to heat it to 30. So we're going to go to here now. So, well, melting is mass times heat of fusion. This is going to be MC change in T. So the total energy, notice we're climbing the ladder. It's going what? Up. So my friends, in chemistry, it's going to be added together. We're not going up and down. Okay? It's endothermic climbing the ladder, right? To go from a solid to a liquid. So it's total energy absorbed. So it's going to be total Q, QT, is equal to what? Melting plus the heating of the liquid to what? Heating of the liquid to 30. So the melting is M times HF plus, well, how do I do this one? Well, mass is the same, right? but this is specific heat, change in temperature. Let's plug these values in so you see what I'm talking about. The mass of the ice is 15 grams. Heat of fusion is 334 joules per gram. I'm going to add this to the mass of the water now. So all of the ice has melted and now is water. Well, guess what? If it's a 15-gram ice cube, it will be 15 grams of water. It's not going to change. The mass, the density and volumes, okay, do, but the mass doesn't. Specific heat of the water, well, we know that, 4.18 joules per gram per degree Celsius. Temperature change. Well, once you heat it, we're right here. Once you melt that ice, it's right here. What's the temperature? 0. We're going to heat it to what? 30. What's the temperature change? You bet, 30. And you plug those in. Okay, so this value gives me 5010. And this other Q, which is heating from 0 to 30, is 1881. These, of course, all joules, right? Everything cancels but joules. This is a degree Celsius. And we add them together to get total value. And I get a total value, an answer to be 6891 joules. 2 sig figs are key here, so obviously we're going to make that answer to be 6900 joules, or 6.9 kilojoules, doesn't matter. Okay, so you can see what we did here. Now we're starting to mix and match or add melting with heating. Let's look at this one. All right, and I'm going to just look at this one. Number 8, count the number of joules required to completely freeze 25 grams of steam at 100. So if we want to freeze some steam, we're going to start with gas, gets cooler, starts to condense, has to become a liquid first, then freeze completely. So we're looking to do 3 things. We have 25 grams of steam at 100. Okay, so we're here first. Then we're going to have to cool it 100 degrees. And then we're going to have to what? Freeze it. So what are my 3 formulas here? Okay, well, number 1, mass times heat of vaporization. That's at 100. We're at a phase change. Then we're going to cool it how many degrees before we freeze it? We have to cool it first. 100 degrees. And then what do you get? Well, this is mass, MC change in T. And that'll go 100 degrees. And then we're going to freeze it. M times H F. So there's 3 parts. And since they're all going in the same direction, releasing, we can add to the total amount. So Q total that's released is equal to these 3 things. Notice the mass, okay, will be constant for all of these because it's not going to change. Okay, so please finish number 8. I would like you to do number 9 as well. Okay, I have a key for that. Make sure you finish number 6, number 5, number 4. Okay, hope that was helpful, and good night.